Hello students, we were discussing the power interface unit between solar panel and load, in which we have seen the DC to DC converter is used between these two to get the maximum power point operation. In that DC to DC converter, we have started our discussion from boost converter, and in boost converter, from the characteristics we obtained, there was some limitation in that. Now let us recall that limitations, then we will proceed to next converter. So the IV characteristics of the system with the power interfacing unit of DC to DC converter, boost converter, was IV characteristics was somewhat this, and the power PV characteristics was this. In that we obtained that this was the operating point for maximum power at the load terminal. It was for the case when there was panel and at the terminal there was an interfacing unit. Power interface unit was DC to DC boost converter, and at the load terminal the load was R0, and this was VT, corresponding the input side resistance or impedance was RT, and this is R0. The terminal voltage is V0, load terminal voltage. And in this case, the relationship between input impedance or input resistance and output resistance was, with the help of the duty cycle, we obtained this was the relationship between input terminal resistance RT and output load resistance R0. And we came to know that with the variation of the D, we can control the power point operation, and it becomes able to operate at maximum power point. But that was for limited case only. There was some constraint in which this was not achievable. So when D was 0, then anyway we will not comment that again, the value of D and so on. So the operating point we obtained in the case of boost converter was somewhat here up to this, from here to here. This was the operating, if it is load line, it is 1 by R0. This is continuous, not dotted. So this is the maximum point of the operation in IV characteristics. Corresponding the load that can be obtained is this. So the range of operation of the power at the load terminal was from 0 to here. This was the power from 0 to this point that can be obtained. In this case, it becomes possible that with the variation of the D, the operating point can be set at this to get the maximum power, okay, irrespective of the load, if 1 by R0 lie between this region. But if 1 by R0, the load connected is load line lie below this, before this, R naught, then the range of power that can be extracted is from here to here. So now at this time the operating point is here, corresponding the power that can be obtained is this. So in this way the operating point that can be from here to here, and let me change this key color. The operating point can be from here to here, corresponding the power can be from here to here. Okay, when the load is R naught, if another load is connected and load line is this, and if this is the condition to get the power, we find that even though we vary the D, we cannot achieve the maximum power point. So this is the limitation of the boost converter. Even though we can vary the D, but we are unable to achieve this point. Now buck converter can help to achieve this point with different R conditions. It may help or may not be, we will see now. So in case of buck converter, the panel terminal is connected with the DC to DC converter, that is buck converter, and the output is connected with the load. Load is not in our control. Now this can be further drawn like this. Here the buck converter can be the combination of switch connected with diode, and after that inductor is connected, and that is connected with capacitor, and the output is connected with the load terminal. This unit is buck converter, which is responsible to control the voltage, to control the operation at this point by controlling the switching operation of the converter. We will see either this circuit is enough or some modification is required, but we will come at that point later. It is switch, diode, inductor, CL and R0. The voltage across this is V0. The current that is flowing here is I0, and the current that is flowing here is IL. I terminal and V terminal. Okay, so this is the circuit with buck converter. Now we will see the characteristics of this converter in this condition when it is interfacing the solar panel and the load. So for that purpose, let us have T and VL, IL. Now if we wish to find the relationship between this VT and this V0, means the input side impedance, that is nothing, the RT, and the output side impedance R0. If we wish to find the relationship between these two, for that purpose we will draw the characteristics of VL and IL. After that we will find the relationship so that we can relate input and output with in terms of D. So let us mark the range of the operation. If we are doing for one cycle, means it is Ts. This is one cycle. The time switching time is Ts. This is the on time, so this can be dTs, and from here to here it is off time, so 1 minus d is off time ratio, and this is the off time in a cycle. So let us analyze the circuit in on condition and off condition. So start from the on condition, means when triggering pulse is given to this switch and the pulse is high, in that case it becomes on, and once it is on, the current starts flowing from here, from the panel, and it follow the path. At this point it is in reverse bias, as the current is flowing from here, it is positive, it is high potential and it is low potential, so it is reverse bias. The current follow this path and the voltage across this is VL. Okay, this is VL that we wish to plot it here and draw it here. So this is the current is passing from here. At this point it has two path. Part of this current goes to the C to charge it, and part of it goes to the load R0. Okay, so during the on condition, the current that is flowing from here follow this path and complete like this. During the on condition, the Vt will be equal to the VL plus V0. Charging this voltage plus this voltage will be equal to this voltage. So if we wish to find VL, then we can say Vt minus V0. Okay, and if this is for during D, then for this period the voltage is Vt minus V0. Okay, that is this voltage Vt minus V0. So we can remove the D, it is not required. For on time the voltage is Vt minus V0, and when the switch is off, at that time this discharges, and this discharges, and the path of the current will be like this, and another path of the current will be like this, and part of it will come through this. Okay, so when it is discharging, again the part of the current will come like this and part of the current go to that. However, once it is off, the current, IT current, don't have path, and it must not break at any value. So for that purpose it becomes mandatory to give it alternative path, and for that purpose a capacitor is mandatory here to store the energy when the switch is off. Okay, so IT now have path from here to charge it when it is off. So for in off condition we have this current has this path. However, in this circuit, VL will be equal to the V naught following the KVL. VL will be equal to V naught. The source is this, that is charged already, and this is a load. However, from here we can say VL plus V naught equal to 0, VL is equal to minus V naught, we can say from here. Okay, so from here during the off period we can have V naught in minus direction. This is V. Okay, so this is the plot, this is the wave shape for VL for one cycle, and after that it repeats the characteristics. Now what will be current? During the on time, this charges, it starts charging and it continues charging till the relation of the, we know VL can be written as L di over dt. From here we can say IL can be 1 by L VL dt, and if we integrate then it can be IL, and from here we find it will be V t minus V naught, V, this is V t minus V naught divided by omega L. So for time being leave it omega L, that is L. So we can say it is inversely proportional to L. It means the slope is inversely to L. Anyway, it is fixed. So once it is fixed, the slope is uniform. So the current have this path from here to here during the charging time, and for discharging time this current discharges and follow the path like that, and at that time the, if we derive, then we will find IL will be minus V naught by L. Again it will be having constant slope with negative sign. So negative slope will be there, and according to that the characteristics will be like this. So this is IL and this is VL during the charging and discharging of the inductor. During the on period it follow this, during the off period IT is 0, and if we talk about the average, then this is IT average. During the on time IT follow this path, IT will be same as IL, and this IT will be sum of this current and this current. This current is I naught, this is the remaining current, the remaining ripple comes from here. So if we talk about the average value of this, then the average of this will give us 0. However, the average of this current will be the average of this D times this current. So we can say IT average will be D times I naught, because this is the only current, this is the current only for this period. Okay, so IT average will be D I naught, and from here if we talk about the relationship between the input and output voltage, we can say input and output voltage relationship then we can say Vt minus V naught times the time of operation plus minus V naught the time of operation will give us sum of Vt is equal to 0 for a cycle, and from there we can say Vt d minus V naught d minus V naught plus V naught d is equal to 0. It will give us 0. So from here we can say Vd is equal to Vt d. Similarly, if we find the relationship between input and output current, in that case we can say IT average is equal to di naught. IT average is equal to di naught. From here we can say I naught is equal to IT average divided by d. So this is equation number 2. Divide 1 by 2, then we have V naught divided by I naught is equal to Vt divided by IT average, d is here, divided by IT average by d is here. It will be Vt by It will be RT d square. This is R naught. So we have relationship from here between RT and R naught. So we can write RT is equal to R naught divided by d square. Now from the relationship that we have, RT is equal to R naught divided by d square. This is the relationship that we can have from here. So D is the control input to get the maximum power point. So let us see how it is possible to get the maximum power point in this case. So if D is 0, so for that purpose let us have the IV characteristics first, then we will IV, this is the IV characteristics. Now at the same time draw the PV characteristics like this. This is the maximum power point. That is our target to have find. Now if this is the load line and this is the operating point, 1 by RT, this is the operating point, and for at this time this is the point of operation, and if D is 0, it means RT is infinite, and if RT is infinite then the slope will be 0. 1 by RT will be 0, and if slope is 0 then the load line can come here. So the point of control starts from here. Okay, so if D is 0, it should be actually small d, keep in mind. If D is equal to 0, then RT will be infinite and the slope will be 0, and V axis will be the load line. Okay, so the control point will come here, point of operation will come here, and if D is equal to 1, that is the maximum value of D, then RT is equal to R naught. Okay, so in this case, if R naught, and for example, this is the load line, and in this condition, if RT becomes R naught, then the point of operation can be this, and this is the power that can be extracted, but this region cannot be achieved. This R naught load is connected. Okay, because the between 0 to 1 only this region can be achieved. So this is the only point region at which the operation is possible, and correspondingly the power can be controlled and can come up to maximum. But if the load line comes like this, in this case 1 by RT will be equal to 1 by R naught at D is equal to 1. If already R naught is equal to RT here, then the operational, this will be point of operation, corresponding power can be here, and only this power can be controllable, as the operation point can vary from here to here. So if R naught is this one, then R naught dash we can say, in that case only this range can be achieved. So what we can obtain from here, this point cannot be achieved anyway with the variation of the D. So just the variation of D is not sufficient to achieve up to this point if load R naught is connected, and in that at that case the operational point is this, means right side towards the maximum power point. So it is important to look for another option in which we can achieve the maximum power point, because there is also limitation like the boost converter. In boost converter this side operation was possible, in buck converter this side operation is possible. So from here if we can concentrate, then we can say if we can operate buck and boost simultaneously, then this region and this region can be combined, and the control can be possible from here to not only here, from here to not only here, but from here to here, full range of operation. And if D can be adjusted, if the operational point can be anywhere from here to here, then D can be adjusted to come at this point, maximum power point, irrespective of the load connected to the terminal of the system.